Welcome once again to our online tutorial classes. Today we are going to focus on electrochemistry tutorial. On the screen is a galvanic cell. A galvanic cell is a cell that converts chemical energy into electrical energy through a spontaneous redox reaction. The reaction in this case is spontaneous. It occurs by itself, unlike electrolytic cell in which the reaction is non-spontaneous because we need an external electrical energy to drive that non-spontaneous reaction so that the current can be produced. So once we have seen that, let's look at the components of this galvanic cell on the screen. We have two half cells here, and in each half cells there's electrode. Electrodes are this solid material. On the left hand side we have the anode electrode where the oxidation takes place. On the right hand side we have the cathode electrode. This one is cathode electrode where the reduction takes place. What is reduction? Reduction is the gains of electrons, while oxidation is the loss of electron. So once we have seen that, also this galvanic cell, the two half cells are connected by a bridge called the salt bridge. It's just a tube that contains either potassium chloride or it can contain sodium nitrate. We are going to see the functions of these ions, potassium ion and chloride ions, or potassium ion and nitrate ions, when we're going to focus on the functions of the salt bridge. There's also voltmeter, and during reaction the electrons will flow from the anode towards the cathode. So that's the direction of flow of the electrons. We also have two different solutions. We have the zinc sulfate on the anode side and copper sulfate on the cathode side. So this type of reactions which takes place here, one is called the anodic reaction, meaning the reaction taking place at the anode side. So here in this case we have the zinc. So the anodic reaction taking place here, it will be zinc will be oxidized. Zinc, which is solid, will be oxidized to zinc 2 plus 2 electrons. So this is aqueous. While the cathodic reaction is the reaction taking place at the cathode, and in this case we have copper 2 plus, which is aqueous in nature, is being reduced to copper solid. So these are the two types of the reactions which takes place. Once we have these two types of the reactions, let's then focus on the function of the salt bridge. So salt bridge plays three major functions. One, it maintains the electrical neutrality between these two half cells. So how does that take place? Remember, at the anodic reaction, zinc 2 plus is going into the solution. So the zinc 2 plus will go into the solution, causing a build-up of a positive charge, zinc 2 plus, a positive charge in the solution. While on the cathodic side, or at the cathode, the copper 2 plus are reduced. The copper 2 ions are being reduced and they are being deposited on this electrode. So here copper 2 plus move into the electrode where they are being deposited, and when that happens it leaves the spectator ions in this solution. However, in this case zinc will then move into the solution, so you're going to have zinc 2 plus in the solution. Now this is what is going to happen. The salt bridge, then in this case we have our potassium. So potassium will exist as potassium ions, and also it will exist as chloride ions. So we have the chloride ion and the potassium ion. So the potassium ion being positive, then what will happen, they will flow to the cathode to balance the negative charge. So we have movement to the cathode side, and this is potassium, while chloride ion, which are N ions or negatively charged, will then flow to the anode to balance the positive charge of the zinc. So due to that flow of ions in which the positive or the cations of the salt bridge move to the cathode to balance the charge, while the N ions of the salt bridge move to the anode to balance the positive charge. So that's how electrical neutrality is being maintained in galvanic cell. The second function of the salt bridge is to complete the circuit, and this is done by ensuring that, look, we have two types of wires here. We have the external one and the internal one. So the external wire, this one here, allows the electrons to flow from the anode to the cathode. However, the salt bridge then, it acts or it completes the internal circuit by allowing the ions to move between the two half cells. And the ions we are talking about here are the cation ions, which is the potassium, and the N ions, which is the chloride ions. So the two helps in completing the internal circuit, as we have seen their flow or the motions. Also, the salt bridge prevents mixing of the solutions. It prevents these two solutions from mixing up, because if they mix up, a reaction will occur and they will build up a heat energy, which we are trying to prevent. So these are the three key roles of the salt bridge in galvanic cell. So we have seen the two reactions at the cathode and the anode, and therefore we can combine the two reactions to come up with the overall reaction. So initially at the anode we said, or at this side we say zinc going into zinc 2 plus 2 electrons, and copper 2 plus is being reduced to copper solid. So the two reactions, this is the cathode, the two reactions can be combined then into one overall reaction, in which we can simply say our zinc, which is solid, plus copper 2 plus, which is aqueous in nature, is going to give us zinc 2 plus, which is aqueous, plus copper solid, So this is the overall reaction of what is taking place. So this is the overall reaction. So once we have looked at this, then we can look at the cell potential. So after this, we can calculate our cell potential of this reaction. So from the standard electrode potential, everything is given in their reduction potential. So we are going to write the way they are in their reduction potential, of which we have copper 2 plus 2 electrons, giving us copper solid, and the reduction or the standard reduction potential of this is plus 0.334 voltage, while the zinc 2 plus 2 electrons, giving us zinc, and this gives us minus 0.763 volts. So this is the standard reduction potential of the two elements. So we need to calculate the cell potential or E cell potential. And cell potential E cell is given by E cathode minus E anode. Sometimes we can say E reduction minus E oxidation, or E right minus E left. So it means that in that case we need to check which reaction is taking place at the cathode and which one is taking place at the anode, and then we get the difference between the two to get our E cell. So here comes a tricky part. If you look at the two reactions, and always in their standard electrode potential, all reactions are written as their reduction reactions, just like they are on the screen. So what you need to do is to look at the standard potentials, these values here. The one which is more positive is the one which is going under reduction. So if you compare the two, we have plus 0.334 for copper, and then we have minus 0.763 for zinc. Plus 0.334 for copper is more positive than the one for zinc. So it means that our copper will remain in its reduction reaction. So meaning that we are going to reverse this equation for zinc so that it can be the anodic reaction equation. So that's going to make this reaction then to be zinc 2 zinc, sorry. So we are going to have our zinc. So we're going to have our zinc then going into zinc 2 plus 2 electrons, and that's gonna give us, so normally when we change the equation or reverse the equation, we normally reverse the sign. So this one will give us plus 0.763 volts. So let's calculate the cell potential. So our E cell is going to be E cathode, and which cathode? We have plus 0.344 minus E anode, and E anode is minus 0.763 minus 0.763, and that's gonna give us a value of, so we have 0.334 plus 0.763, and that's gonna give us a value of, so I'll push everything up here, and that's gonna give us our E cell to be 1 point. It's gonna give us a cell of positive 1,097097 V. So this is the E cell. It's very important to write the sign is either positive or negative. If let's say the same person write 1.097 V without indicating the positive sign, then it is wrong because we don't know if it's negative or positive. So you may ask yourself, but we reversed the reaction for zinc, but why are we still putting minus here? This is the conventional. We say the E cathode minus E anode. We are still going to maintain the standard potential for the anode for zinc the way it is given, and that does not make change. Or even if you use this one, if you reverse the sign, it will still give you the same value, and in this case we are going to say E cell, in that case will be E cathode plus E anode. So that's going to give us plus 0.334 plus 0.763, which is still gonna give you this answer. Even though you are reversing the one for more negative to be oxidation reaction, you don't need to change its symbol or the sign for its standard potential when you are calculating or when you are inserting it in this equation. So we have seen in these reduction potential values that copper is more positive than zinc. And what does that tell us? If copper is more positive than zinc, so that can tell us either one is reducing agent or one is oxidizing agent. If you look the standard potential values, copper is more positive, and because it is more positive is the oxidizing agent, and an oxidizing agent is likely to be reduced, and in this case we have our copper. Oxidizing agent is the electron acceptor, so it accepts the electron and itself is the oxidant. So in this case our oxidizing agent is copper. And if we look at the reducing agent in this case is going to be zinc, because zinc has the more negative value of the standard electrode potential, and in this case our zinc, which is the reducing agent, is likely to be oxidized. So remember, reducing agent is being oxidized, so reducing agent is oxidized, while oxidizing agent is being reduced, itself is being reduced. So we are saying in this case our reducing agent is zinc. So our reducing agent here is zinc because it has more negative standard electrode potential, and because it's a reducing agent we can still call it as a reductant. And also reducing agent is the electron donor. It donates electron to you can be given an equation and you are told to balance it in acidic solution. So in this case, for example, we have, okay, let's put the arrow here. So we have manganese on the manganate oxide we have on the left hand side, and we have Mn2 plus on the right hand side. We have oxalate ions giving us CO2. So the first thing that we need to do in this case is to write the two halves reactions. So we can divide them into MnO4 minus to Mn2 plus, and we can also look for oxalate C2O4 2 minus into CO2. So once we have done this, the next we have separated the two reactions into two half reactions, and then what we can do is to help us calculate the charge. So let's calculate the charge of manganese on the left hand side and zinc. So how are we going to do that? So we have, I'll do this on this side. So we have manganese MnO4. The overall charge here is -1, so we have to calculate the oxidation state or oxidation number of manganese. So let's call it X. So it's going to be X minus 4 atom of oxygen, sorry, plus 4 atom of oxygen into the oxidation number of oxygen is 2, and that's going to give us -1, the overall charge here. And this is going to give us X minus 8 plus 4 times -2 is -8 is equal to -1, and that X is going to be -1 plus 8, because this crosses the equal sign, it's become positive, and that's going to give us X to be +7. So it tells us that the manganese ion here has a charge of +7. So it has gone from +7 to +2, and it has reduced. Okay, so the charge has reduced. Let's look for the carbon, the one for carbon. So on the carbon, we will need to check the oxidation number of carbon on the left hand side and the carbon on the right hand side. So let's see carbon. So we have two carbons there. So we're going to say 2x plus 4 atom of oxygen, 4 atom of oxygen times -2, which is the oxidation state of oxygen, is equal to the overall charge of the oxalate here is -2. So that's -2. So going to be 2x plus 4 times -2 is -8 is equal to -2, and 2x will be -2 plus 8. So 2x is equal to +6, and that's give our value of x to be +3. So it tells us that the carbon here is +3. And let's look at the carbon on the right hand side, this one. So we're going to say our x for this one. So we are calculating for that. So our x plus 2, there are 2 atoms of oxygen, in bracket -2, which is the oxidation state, oxidation number of oxygen, is equal to 0, because the overall charge here is 0. So we're going to have x +2 times -2 will give us -4 is equal to 0. So our x is equal to +4. So making this our carbon here to have +4 as the oxidation number or oxidation. So once you have calculated, so we have seen, so from, if we look at manganese, so manganese has moved from +7 to +2, so the oxidation state has decreased, so meaning that it's being reduced, while the oxidation state of carbon has increased from 3 to 4, so it has gone up, so it has increased, so meaning it has been oxidized. So this one goes under oxidation, while this one goes under reduction. It has been reduced. So from here then we can proceed by looking at or balancing. So the next thing we need to do is to balance all the atoms except oxygen and hydrogen. So if we look manganese, we don't need to balance manganese, because we need to balance all the atoms except hydrogen and oxygen. So in this case, we are not going to balance manganese, but we'll look at the oxalate. On this side, we have 2 carbons. This side, we have 1 carbon. So we can put 2 there to balance the carbon. So our carbon is balanced. So we have balanced our carbon in the oxalate. So we have 2 carbons on both sides. So after this, then we can balance oxygen. So we need to balance oxygen. If we look at this equation, the one for oxalate, oxygen is balanced. We have 4 oxygen here, we have 4 oxygen here. So we only need to balance oxygen in the first equation, the first one. How are we going to do that? We add oxygen, or we balance oxygen by adding water. So we are going to add water molecules equal to the number of oxygen atoms present. And if you look on the left hand side, we have 4 oxygen atoms. On the right hand side, we don't have oxygen atom. So we are going to add water molecules equal to the same number of oxygen atoms on the side where we have less number of oxygen. So in that case, it is on the right hand side. So we have 4 water molecules. So once we have 4 water molecules, then you see in this case, we then introducing hydrogen. So we need to balance this hydrogen here to the side where there's less hydrogen. And in that case, we have less hydrogen on the left hand side. And how many hydrogens do we have? We have 8 hydrogens, because 4 times 2 is 8. So we're going to add 8 hydrogens on the left hand side. So we have 8 hydrogens. So once we have 8 hydrogens, then the next thing that we need to do is to balance the charge. So let's see the charges that we have. So on the left hand side, we have 8 protons, which is 8 plus minus 1, so we have 7 plus. On the right hand side, we have 2 plus. On the manganese, water is neutral, so we don't need to do anything on water. So it means that on this side we have plus 2, and on this side we have plus 7. So we are going to need 5 electrons. So we're going to need 5 electrons. When we add to this, then we are going to remain with positive 2 on the right hand side. So meaning on this side we are going to say plus 5 electrons. So we're going to have 5 electrons. So let me just write it down here. So we're going to have 5 electrons plus 8 protons plus manganese plus, okay, manganese. Then now we can go to Mn2 plus water, and then here we still maintain we have our C2O4 into 2CO2, but then here it was 2 minus. If you look on the oxalate, the charge is not balanced, so we can balance the charge. So the overall charge here is 2, and on the left hand side, on the right hand side, it is 0. So we need 2 electrons to balance this, because 1 electron, 1 carbon is -1 and another carbon is -2. We have 2 carbons here, so you're gonna need to have 2 electrons. So once we have reached at this point, then what we need to do next is to balance. So if you look at the first equation, the one for manganese, we have 5 electrons, but on this side we have 2 electrons. So we need to balance the charge, and we are going to balance the charge by multiplying equation 1, this is our equation 1, by 2. So everything we are going to multiply by 2, while equation 2 we are going to multiply by 5, so that, because 10 is, in this case, 10 is the LCM, the least common factor that you can use between 5 and 2 to balance the charge. So in that case, you're going to have 10 electrons plus 2 times 8 is 16 H plus protons, plus 2 times MnO4, we're going to have 2 MnO4, and that's going to give us 2 Mn2 plus 2 times water here. Okay, this was 4 moles of water, so we're going to have 8 moles of water. And equation 2, 5 times 1, so we're going to have 5 C2O4 2 minus, giving us 5 times 2 is going to give us 10 CO2 plus 5 times 2 is going to give us 10 electrons. So we have 10 electrons in this case. So once we have done this, we can balance the charge. So we have 10 electrons and 10 electrons, and they cancel each other. So remember, we are balancing it in acidic media. So from here, we can just combine the two reactions, and If you look, there's nothing which can cancel each other in this case, so our equation is going to be 2. So overall is going to be 2MnO4 minus, so this minus was still here. Let me just put it, plus 5 C2O4 2 minus plus these 16 protons, so 16 protons giving us 2 Mn 2 plus 10 CO2 plus 8 moles of water. So this is the reaction in, or this our reaction in acidic media. So this is what happens in the acidic media. So let's look what can happen in the basic media. So assume that now we need to balance this reaction, the same reaction in our basic medium. So what you need to do, assume that the reaction is in acidic medium. So you can do it until this point where you have your acidic media. But now when you are balancing it in basic media, meaning that you are going to introduce OH minus. So the number of OH minus you are going to add is the same as the number of the protons that you have in your acidic media. So in your acidic media, I've written this equation here. It's just this equation from the acidic media. And in the acidic media, we have 16 protons. So we are going to add 16 OH to balance these protons. And that's going to make us have 2Mn plus 5 C242 minus plus 16H plus 16 OH minus, giving us 2Mn 2 plus 10 CO2 plus 8 water molecules plus 16 OH. Okay, so that's what we have. So now we need to add everything. So 16H plus 16 protons plus 16 OH is going to give us 16 water molecules. So we're going to have 2MnO4 minus plus 5C2O4 2 minus plus, so now we have a total of 16 water molecules, giving us 2Mn2 plus, this is not part of what we are writing now, plus 10 CO2 plus 8 water molecules plus 16 OH minus. So if you see on the left hand side, we have 16 water molecules, and on the right hand side, we have 8 water molecules. So what we can do, we can rewrite this equation by subtracting or cancelling out what is on the left hand side or what is on each side, which are the same. We need to subtract the least from the highest. So in this case, we have 16 water molecule, and on this side we have 8 water molecules. So what we can do, we can subtract 8 molecules from 16 molecules of water, making us to have 2MnO4 minus plus 5 C2O4 2 minus plus, so now we are going to have 8 moles of water, giving us 2Mn2 plus 10 CO2 plus, so this side we don't have water molecules anymore, but you're having 16 OH minus. So this is our reaction in basic media. So it's not as challenging as it looks, but the most important thing is to write your equation or balancing in the acidic media. And once you have reached at the acidic media, you're going to realize that you have the protons that is remaining. So what you need to do is to introduce OH or OH minus ions, hydroxide ions, to balance it in the basic medium. And the number of OH minus you are going to add is equal to the number of protons that you have. So in that case, you are going to have water molecules on one side and water molecules on the other side, and therefore you need to subtract or to make sure that they appear on the same side, and you can do that to cancel them out. And that one also, you need to check for all other molecules or atoms, especially the molecules which appear on both sides. You need to collect them to one side. So that marks the end of our tutorial today. I hope we try to solve some of the questions. Thank you so much. Hi, remember to subscribe, like the video, and share with your friends so that each and every time we make new uploads, you get notified. Thank you so much. Bye.